Good morning. Let's do a talk on introduction of transforms in signal processing and how does this simplify the complex problem. That's what we're going to talk today. So basically, let's start with what is transform. What are the transforms? They are basically mathematical operations that convert the problem into simpler form to simplify complex calculation and analysis. So essentially, we can do a calculation by own means, whatever we have learned from the beginning. But to do the complex problem, it needs a lot of um, efforts to do the analysis. So let's see how we have done this earlier also in the basic classes. So in the basic math, we use the logarithms, and this was also transformation to do a simple basic mathematics, and then we will extend this concept to the signal processing. So let's see how does this multiplication in transform domain makes the life simpler. So simplifying a mathematics with the logarithms is one of the concepts. The multiplication is a complex, especially with the large numbers, and it becomes very tough. What the logarithm does is convert the multiplication into addition. For example, let's say I want to multiply 1000 by 10,000. Now, if I use the logs, what I'm doing is our problem was to multiply the 2000 by 10,000. And then what we have uh, done is rather to multiply this, we are doing a kind of mathematical operation log. So log of 10,000 into 1,000 into 10,000. Now, without going to the explanation of why it happens, is what we couldn't accept, or you might have already known it, that the multiplication of the two terms, when you take a log, is basically the addition of the two. So if I can know the log of 1,000 and the log of 10,000, I can add this. So the multiplication has reduced to addition. And so the calculation has become simpler. So, but then what is a log? Log is basically, when you talk, it is a to the power x. Let's say there's something exists, a to the power x equal to b. This is represented as log of a to b is equal to x. So it's something, what we're saying is, given a number, if I take the log of the number b for this number, what is the power by which this comes out? So basically, log of any number is the power to this number. So when I have got a to the power x, this will result to b. So for example, let's say log of 10,000. So what we know is 10 to the power q is equal to 10,000. So in this case, the log of 1000 to the base 10 is the power 3. So essentially, if I want to do the multiplication, what we were talking was, if I have got 1000 multiplied by 10,000, so this is, if I take the log of this to the base 10, so then this is 3 plus 4, which is equal to 7, right? And so what you have is, the answer to this problem is then 10 to the power 7. Well, It's a simple math. So what you can know is this is 10 to the power 3 and that's 10 to the power 4. So if I do this, it's 3 plus 4. And that's the answer is 10 to the power 7. So that's a simple thing that what you do is what you can see from here as well. The only thing that we have proven here is that, well, if I take the log, it's going to be very simple. Now let's go into a bit complex kind of problem. And the problem here, what we're taking is, let's say I am trying to multiply 15.27 multiplied by 684.43 multiplied by 73.56. Now, if I want to do this multiplication manually, it's going to take a hell lot of time. Forget that you have got a calculator or a computer. Let's say if I want to do it, think of the person when people are using it without them. So what they did was they created a table of the logs. So here is a log table, a sample which is over here. And for example, if I want to know the log of 15.27, so I have got 15 over here, this 15, then the 2, right? And then the next is 7. So the 15.27 is, well, this is in tens. So we first write down 1 less than the power. This is basically uh, two zeros, or before this is 2. So we'll write 1. The rest is, it's a simple thing that what we do is um, we have got the numbers 18. I'm sorry, this is 18, 18 plus the number here is 20. So add it, add the 2. So this become 1838. And if you see this log over here, this is 1838. That's precisely is what we have done over here. So using the table, I can get the value of the log. Similarly, if I want to do it for 68.684 point this, so there are 3. So we'll have 2 here, right? So one thing that is very clear is that what we are going to have, there will be something 2 point something, right? So there, if you go down, if I keep going down, 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 I'll be getting somewhere here at 68. Then you have got the additional term 4, 4. So then you have to do the same thing what we had done it. So 68, and then I have got 4. So 68, 4, and then again 4. All right. And if you want to take 3 also, in that case it is to shift and added. So that's a simple log that you have done it. So using this, anyway, we get the 3. This is one, this is what I said to you is that there are 2 digits here. So this is 1. There are 3 digits, so 2. There's again 2 digits, so 1. I'm using the same thing we got the logs. And now if I want to multiply this, so it's basically actually an addition of the numbers. So this all added together, this becomes 5.885. So now we have to go for anti-log to get the value. And if there is 5, so this will have a 6246. That's one reduction over done here. So this one will be added over here, right? This is called the characteristic part. And then you have to basically, essentially, you have to see that 8857. And once you see the anti-log here, this is the anti-log table. Well, I have taken all of them. So here is the 8, 8, and then you have got 5, and then here you have got 6. So this is the 8, 8. You have got the total value is uh, addition of the numbers is 8857, right? So you have to do this 885 and not 6, it should be 7. So take this and then do add it the same way and you get the answer. So what you have seen from here is a simple thing. A simple thing that what we said is if you have got some operation to be done, in that case, the best thing that you have to do is you can use a transformation. And the transformation is a mathematical operation that converts the problem into simpler problem. That's what we started with, and this is what we are saying it again and again. And the simple thing that what we're seeing is the logarithm. Let's see how does it go if I go for the signal processing, what this is, and how does the mathematical operations on basic signals can change. The first thing that we need to understand is what is signal. Signal in Hindi is said sanket, or when you say he's signaling. Let's say if I say like this, try to understand if somebody says like this, that means he is calling you. If he says like this, so he is saying go out. So this is the symbol that we are, or the signal that we are making. It conveys some meaning. Now, if I talk about the the signals in engineering, is actually data information that varies with the time. For example, audio, video. Well, we'll be talking about the images rather than video. Video has got the images which is changing with the time. Well, time is one of the notions which is always there. Processing means analyzing, modifying, or extracting information for a signal. The signal often needs to be transformed to be effectively be processed. So, the use of transform signal processing is to simplify the analysis of signal, extract the useful features from the data, convert the signals into a form that is easier to work with. For example, the frequency domain, we'll be talking about that. And the type of transforms that you normally get is a Fourier transform, Laplace transform, jet transform, and so many. Weber transform, and keep going. So it's a mathematical operations. You can always come up with some new way of transforming the numbers. Right. For example, Fourier transform decomposes a signal into a constant frequency. Now, what does it mean is we will be talking in short time. And it provides the frequency spectrum for signal, that how many, what are the different frequencies that are available in that signal. The practical application includes the audio processing, image processing. That's what we will be talking, something in depth. Audio processing is the one what I am talking is, you might be getting whatever I'm speaking. If you feel there's a noise, there is some signal which is not desirable is the noise, and then what you have to identify from the audio signals is get these things identified and removed. All right. And so on. The communication system has modulation, demodulation, control system, has stability analysis, and system response. All can be done using this. Is all actually a signal, and we're trying to do a signal processing this. Now here I am coming and trying to do something very interesting. That's trying to understand what signal is. Signal is a very conceptual thing. Let's say if I want to talk here about you might have seen the sockets. So let me go back quickly. Normally you might have seen this socket, and that's something called voltmeter. So how much voltage that it is giving, if I connect this device across it, I will see the voltage. And that's your common bulb, the tungsten filament lamp. So if I connect my filament, it will have a current is passing through this, and so the filament gets heated up, and you will be seeing the illumination. And there will be a voltage which you will be seeing here. This is normally in a AC one and measures the RMS value. We are not going to talk about that. Now, forget it, and let's try to see that if I can presume that this is going to be measuring very quickly and I can see that very fastly. So if I try to analyze, I see this, what happens is at time equal to 0, it has got some value, let's minus 5 volts. At this time instant, mind this is in milliseconds. So we are presuming that while we can see it in milliseconds, the voltmeter readings. Now this voltmeter is going to change very swiftly, whatever the value of the voltage is. So initially it was 0. At this time, this becomes minus 2.5. At this time, it becomes 0. Then it goes positive. Then some positive value 2.5, then 5, then increasing. So 0 to 2.5 to 5 to 7 to 8, 9, and then goes to 10. And then from 10, so you can see from 0 to 10, in certain time it has risen. And then from 10 to, um, we are not precisely seeing the 0, but then what we can see is it has gone to a very small value, minus 1.22, and then subsequently it has gone negative. And it goes on, and it goes to the, here was a positive peak, there's a negative peak, and so on. So if I plot this is something like this. What does it mean is, at equal to 0, there was a voltage. For example, let's say there are two voltage and currents. So the voltage is some value here minus some value, as I said. At equal to 0, at some time, it has gone to 0, and then it has gone all the way to 10 volts, then coming back to 0, and then it has gone to negative, has got a peak, and then it comes back. So the signal is changing with respect to time. All right, this is the time which is converted into the angular frequency. That is again where none of our concern. So let's come back to the signal passing, where we're talking about is that, well, it has got some kind of signal like this, right? So as time varies, the signal has got, they are basically the numeric values. As we have seen it here, essentially they are all numeric values. It is nothing beyond than this. If I measure it, I take a copy myself and try to record it. I can create my own table, all right, and put here, take a logbook kind of thing, and I put here time, and the another place I put, oops, sorry, that's my time, and here is my amplitude or whatever, the voltage of the amplitude. And so I keep writing down the values, and what we get is this table. All right. So this is my signal values. That's my signal, and signal here is a voltage. And this signal is a time varying signal because as time changes, the values are changing. And we normally write down by an expression. Let's say I write down as this, because this is a variation. What we have seen is a sinusoidal. It is looking like a sine wave. So we attempted to represent it. You will be there are a lot of techniques by which you can write down this. So even if I don't know, I can take in the different curves and try to fit in the values and see to that what kind of equation that I get. So as signal, what you get is represented is varying the time. That's good enough. That's your sensory measurement. So what the sensor over here was essentially, um, uh, in this case was, um, in this case was a voltmeter. All right. So I have got a voltmeter and I am seeing it through my eyes and recording it on the table, right? Time versus this, and noted down the values and then plotted it, and that's what I get. But then I have got another thing which can be really interesting is I normally see kind of waveforms which is varying in space. For this is an example, this is a time. This is a staircase where I have got the step changes all across and keep going. So if I am representing this, that's a space variation. It's actually varying the space. Now I can see this. Now here comes the main problem. If I have got a step kind of wave, I am trying to represent it. So let's say the simplest thing what I can do is, uh, let's say if I say, well, this is a kind of, that's your step that you are trying to make every time. Or if I make it periodic, in that case, I can say, let's say if it is like this. So people wanted to see this, how to write an expression, and particularly we wanted to do it in terms of sine and cos. Why the sine and cos is because of the fact that sine and cos they are varying very smoothly, right? Or the other thing that what normally people say they are a term used in mathematics is a differentiable function. What the differentiable function is, you have got a change which is not a step or a abrupt change, but it's a continuous change. And I hope you remember the continuity, the differentiability, all this, that's what we have talked. So you actually define dy by dx is equal to limit delta x tends to 0. That is for a very, very small thing, what the change in y with respect to x is called the dy by dx. So if I take a sign that say a continuous differentiable form, whereas if I take this, it's not. So the idea is, can I generate this using sine? And one of the famous theorems that so what we talk is called the Fourier series. So let's do it. Can I expand this kind of waveform in terms of sine? So I take it a 2D case, and in that case, I'm trying to do this staircase mapping. So if I plot a simple sine, just this value, what I get is this. When I add this term, so if I add this sine 3, I get this, and what you can check here is there are three ripples. So that's your triplet frequency, that's what we call it. And if you add the 5x and the 7x all together, now you can say this is now creating more or less like a staircase, one of the steps. So what we have is, if you try to see this in a 3D case, it is looking something like that. I have got a staircase which has got, all right, and it is coming back. All right. So that's your staircase in the other sense. That's what we are trying to create. So, well, I can, in general, add the sines and cosines, right? And they have got varying frequencies, and the frequency is the this is your wave number. That's what we say is the wave number 2 pi by lambda, and lambda is called the wavelength, right? So that's a wave, and I can create the wave number by 2 pi by this. So I can create multiple wave. Uh, this can also be thought as a uh, we can take, for example, you can imagine there is a cloth, and this cloth is being excited by the humans. That, let's say I have got 2 or 3 persons sitting. This guy is running with sine kx only. The another guy is running with sine. That's not exactly this. Let's say sine 3kx. The another guy over here, he is pulling this by sine 5kx, and this guy at this another is putting it by sine 7kx. And I want to see what is the shape of the. I am interested in shape of the cotton, cotton sheet. All right. So these are the frequencies by which I am. This is at fundamental. There's this is fundamental. We normally call it. This is the third because this is third harmonic, right? And so is the fifth and the seventh. So this, what will the shape of the cotton? Well, roughly saying, not exactly. So that's what you're going to get, all right? So this is also trying to say that, well, how can the addition of the number, the Fourier series, can be understood physically? Is that if I have got multiple excitation which are of the different natures, here as is shown at the bottom, they will be adding up to like this. We have taken this staircase, so let's try to take a 2D case of this, where it is amplitude versus time is now varying as this. So I have seen this as a different signal is time varying. I can put, rather than time, I can put a space also here. It doesn't make any difference. Only thing is here, what you say is the frequency is 1 by t. If I talk about the space, then this will be 2 pi by lambda is the wave number. So either I plot it by frequency or by the wave numbers. All right. So that's how does it goes into. So if I do and try to understand what are the frequencies, as here we have taken here only 1, 2, 3, 4, four components: fundamental, third, fifth, and seventh. If I add how many frequencies that I have to add and of what value, you can see here that the amplitudes are not the same. This is a fundamental, this multiplied by A, this is 0.33, this is zero point 0.2, this is 1.15 nearly. So the amplitudes are also not the same. What I mean to say is this guy is putting in the whole huge amount of efforts. This is doing only 1/3, this is doing 1/5, this is doing 1/7. So the forces that are being exerted is not equal, and that's another big problem. That's so one is pushing very heavily, the other is pushing uh, slightly low but at a different frequency. He is doing still at a lower but another at a very high frequency. So that's we want to see what are the amplitudes and the frequencies which will be needed, so that if I add all of them I can get this. And so this is called the frequency spectrum. So that's your half staircase waveform. And if I try to find out, I have done it using MATLAB. You can see that there's a DC value, there's no frequency, and then I have got all the continuous lot of frequencies which are needed. So the number of frequencies that is needed to be added, all signs minded. So all signs when you add it together will give rise to this. That's your signal processing. How does it really impact? That's what the thing is. Let's come to a two-dimensional signal. Well, this was also a two-dimensional signal. I have got X, Y, and the Z. So in the same way, a two-dimensional over here is X. What you can say is that's my x-axis, that's my y-axis, and the pixel values, as you know that this whole image is nothing but a grid. It's having uh, is a kind of grid, and these are called the pixels. So the pixels have got different values, right? And they add together to give you a image. All right. So this is a sequence of pixels arranged all across the area. What we are doing here is a histogram, that is, uh, I'm just trying to see, let's say this is having some brightness, this also has the same brightness. So the two have the same brightness. All right, the intensity, let's say 100, I count how many pixels are there, all right, and so on for the whole. So let's say what we can see here is that the pixel intensity is varying from some value to less than 250, and has got that's my if I do this, that's my spatial analysis. I am trying to describe this image and analyze it by a method called spatial analysis. Why spatial is in space you have got these pixels and I want to find out what pixels have got what values, right? Nothing beyond it. And I can do this, I can do a histogram, a lot of operations to modify the image. Now coming to the frequency domain. We have seen this the scale or the grayscale image over here of the Lena. That's a very famous image in image processing, what we talk about. Now, what we are doing here is we have divided into the two frequency components. The frequency varying along one direction and the frequency of varying in the other direction, and we have plotted this. So 0, 0, if I want to do this, that you can see here is this is 0 and there's another 0 over here, so that's another 0, right? So that's your plot where I have got two frequencies, all right, one in the x direction, another, well, there's not no more x direction, the frequency that we are talking here is in a different domain altogether because it's non-existent. So let's call it U and B. And the interesting segment here is not this, but the interesting segment is if I if you see this central area, the best part is the red has got a highest value. So some component, if I transform this, how we have gone into this is something we are going to talk later. So what we see is the lot of values are sitting here. Then the yellow one is having very low values, so the low values are lying here. And if you go beyond this square, all of them are blue, so they are almost going to be in zero range. So the effective information that is of concern is in this frequency. So we are now no more interested. If I see the image, we are interested in this component only. Using this is what we call it as called a JPEG or JPEG compression that we normally employ to this. So given any image, you do a transform called DCT, and then you use the DCT. We are not going to. This is the formula. So it doesn't matter whatever is the value of fxy is the value of the intensity value at coordinate x and y multiplied by this. We have taken a subblock area of 8 cross 8. So essentially, we don't take the whole image. So we take a small segment of 8 cross 8, then followed by 8 cross 8, 8 cross 8, and so on. And then this is the spectrum of the complete one. Well, the JPEG doesn't do that. So it has got the small sections of 8 cross 8, and then it represents through quantization and this. So essentially, uh, we also do the filtering, that is kind of the low pass filtering, wherein you try to smoothen uh, the you want to blur it. So in case you have got any steep change, any steep change is abrupt change, as we have seen, and it's a high frequency component. So that's all for today, and we'll be talking once again about the concept further. Thank you for watching me.